All right, section 1.2 is going to start us into the first calculus, truly calculus concept. Everything we were doing in the last section is related to calculus, but it isn't things you've never seen before. If you've not taken any calculus course before, this concept is something you probably have not seen anywhere before, and it's the concept of limit. So let's start with defining loosely what a limit is. A limit is a y value that you get close to, but you may or you may not actually arrive at. You may or may not actually touch it. Now the notation for that, there's 3 different notations. I know you guys are writing some of this down, but what's the difference between the 3 notations you see there?
From which direction you're approaching the limit?
Yes, and in terms of the notation itself, what difference are you seeing? Right. It's whether or not there's a plus, a minus, or nothing after that number 3. Does everybody see that? That's the only difference between the 3 different notations that are listed there, is whether there's a plus, a minus, or nothing written after the X and the arrow. All right, so this notation, I'll just take the first one. This notation has this meaning, but not only does it have this meaning, this is how we read it. So when I look at this, I say this is the limit of the function f of x, or of f of x, as the value x approaches 3. The plus sign means from the right-hand side of the graph. And if you think about that, that's because the positive values are on the right and the negative values are on the left. So we associate the right-hand side of the graph as being positive and the left-hand side as being negative. So this x approaches 3, positive means 3 from the right, because the right is the positive side. And the negative means 3 from the left, because the left is the negative side. And the last one doesn't have anything written after it, which means you have to be able to do it from both directions, from the right and the left at the same time. Can I go to the next slide? Are we all good? The next slide actually talks about when limits exist. Limit existence. A limit exists if and only if both corresponding one-sided limits exist and are equal. So if I go back to that previous screen, what that's saying is that that third one down here, this thing is only going to be possible if the 2 above it exist. They actually have a value, and the values are the same. They match. Now, we're going to come back to that as we look at the first example so you can see how that actually plays into what's going on. You guys ready to try that first example? All right. This should look pretty close to the image on your paper, does it? Look okay? All right, great. We are going to take a look at some limits. So the first one right here, they talk about has the value x approaching the number -1. Don't get confused with that positive regarding the number itself. The x value is -1. So the x value on my graph that I'm looking at is over here, right, at x equal -1. However, this plus sign over here means from the right-hand side. So I'm going to use red, and I'm going to put a dot somewhere on the graph's curve that is to the right side of the x value. There's nothing special about the place where I put this red dot. What matters is that it's on the curve. Okay, the curve means the actual graph of the function itself. And that the x value at the place where I put that red dot is a bigger value than the x value I'm trying to get close to. So if you put your red dot over here, or if you put your red dot right here, any of that's fine. It just has to be a red dot that is to the right, that is an x value slightly larger at least, than the value x equal -1. Okay, is everybody good with that? Okay. So that's the first thing, is that I want to take a value somewhere to the right of this x value. The next thing is that this arrow means that I'm supposed to approach this x value. I'm supposed to move towards the x value of -1 from wherever it is I start. Okay. So I want you to imagine yourself standing on top of the red dot. Okay, can you put yourself in there? Can you picture it? You're standing there, and you're supposed to start walking along the curve. If you're walking toward the x value of -1, are you going to walk more or less to the left or more or less to the right? You're going to be moving left, because this is the direction that will get you closer to an x value of -1. Okay, so you're standing on the red dot and you're moving along the curve in this direction. Is everybody good with that? The question that you're answering then as you move is, what y value are you getting close to? The x value you're getting close to is -1. What y value are you getting close to as you approach that x value? It's 2. Now the physical location you're getting close to looks like a circle with nothing filled in, right? So you're not ever actually going to get to y equal to 2. But you're going to get as close as you possibly can because you're getting close to that filled or that empty circle. It's not filled in, that blank looking circle. That blank looking circle, however, appears, at least on the picture, to have a y value of 2. Is everybody good? All right, we're going to do the same thing, but now we're going to do that from the left, right? Same x value, but I need to start slightly to the left of it. So I'm going to put a green dot somewhere over here on the left. Now you're going to be standing on the green dot and you need to be moving towards x equal -1. So in which direction are you moving? To the right. So this is the direction you're moving in, and as you're moving in that direction, what y value are you approaching? 1. And you're actually on the y value the whole time, this time, right? And that's actually different. But it's the same limit. It's the y value you're getting closer. You just get to get there this time. You actually arrive at the correct y value this time. All right, so now what is part C asking you? From both sides. Now, that's the same question that happens over here. This says the limit exists if and only if the corresponding one-sided limits exist. They do, right? They both existed and are equal. And these are not. These limits, the limit from the right and the limit from the left, do not equal one another, and so this limit does not exist. Abbreviate D and E. It doesn't work. Right? So if the red dot is myself and the green dot is my husband and we're both approaching this value, we will never meet. Right? This is like me saying I'm going to Chili's in Shawnee and my husband thought Midwest City. That's a problem. We will not eat dinner together, or it will be much later, right? Okay, it doesn't exist. All right, we're going to take a look at the next two. They're done a little bit differently, only in the sense that you don't see any pluses or minuses to compare to first. So let's say instead of sort of developing what's from the right, what's from the left, does it exist at that point, we just jump into what's the limit at that point. Okay, so the x value itself for this third one, or this part D, is -2, which is right here, yeah? And the point actually on the curve is right here. So this is the location. So I'm supposed to do the same thing that I did on part C. I'm supposed to approach this value from both sides. Everybody good with that? Okay, so I'm going to do that red dot, green dot that I did before. The red dot can start anywhere to the right of the value x equal 2. So I could still start my red dot over here. The difference is that I'm going to still move to the left. And when I get to that open circle, I'm just going to jump. And I'm going to keep moving to the left. Because I haven't gotten to x equals -2 yet. So I'm just going to make the jump and I'm going to keep moving. Okay? If you happen to start your thinking already over here closer to x equal -2, you don't actually have to make the jump. That's fine. It still results in the same thing. And then the green dot, the one that's moving from the left, starts over here somewhere and moves towards the right-hand side. Do those two sets of arrows lead you to the same location. They do. What y value are they leading you both to? 1. So this limit exists and it's 1.
So what makes that different from the does not exist limit?
The limit when it was does not exist, visibly what happened is that as we were moving to these locations, we actually both get stuck in a different spot.
Okay.
Because that x value has a jump in the graph at that spot. One direction it moved towards 1, and the other direction, 2, and the other direction it moved towards 1. So we don't actually end up in the same location. When I'm approaching x equals the -2, I actually make the jump to here because I'm not at x equal -2 yet, so I continue along the curve and I actually get to the same place on the
Oh,
curve.
okay.
That's what's different,
Okay.
is that I'm actually able to get to the same
So
location.
the end of one limit was -1, so it wasn't able to.
Yes,
Okay.
exactly.
But
That's
you can
exactly
only
right.
make that jump if they are on top of each other on the same x value, correct? If they're on 2 different x values, you can't jump.
Yeah, you wouldn't be comparing them if we were comparing 2 different x values. Yeah, we're always going to be approaching the same x value. And it might be easier for some of you to simply think that our red dot, I don't know what I would do, simply starts closer. I simply started closer to the point that I was to begin with. So you don't want to think about, do I make jumps or not? Just make your x value start close to where you were starting, to where your concern is anyway. And then the question still, as they move inward, do they get to the same location? And in this case, they did. All right, we have one more in this picture. It's the x value of 0. So the x value is actually the y-axis, right? We don't move left or right anywhere. So the location of my curve is right up here. I'm somewhere in here. So let's not worry about jumping again. Let's actually just start close enough that I don't have to make any jumps. So if I do a red dot on the right and move towards my x value of 0, and a green dot to the left, close enough that I'm already on the same portion of the graph, and I move towards the x value of 0 on the right, first of all, do they approach the same location? Yes, they do. They do approach the same location. What does it approximately look like it is? 2.8, that sounds like a good estimate. If your estimate's not the same, that's fine. You're still in the ballpark of 2.8. We're all in good shape. So I just put an approximation because we kind of guessed at it a little bit. But it definitely exists, right? It's definitely getting close to the same place on the graph. Any questions on this imagery?
So even if they're not like the same, because it has to be equal, even if they're not on the same going towards it, it's just the fact that the point is equal, right?
Ask me one more time. I want to make sure I'm hearing your question correctly.
Like, because you have one come from the right, one come from the left,
Mm-hmm.
but on a curve, they're not the same values going into it.
That's true, but they're getting close to the same value.
Right, so like the end point is
Yes,
equal. Okay.
exactly. That's exactly right. Yeah, whereas like on the left side, when we did it for part D, it was straight, so all the y values were 1.
Right.
So it's very simple to see that that makes sense. But yes, on a curve, same idea. It doesn't matter that the y values are different as you approach.
Mm-hmm.
It's that the y value they're getting close to is the same. Mhm. Any other questions on this idea? Okay, we're going to keep working with this idea. But the next one that we're going to work with, just a sec. Okay, so this is actually, this question is going to combine a little bit of what we did in the last section with a little bit of what we just did on this picture form a minute ago. So this talks about numerical limits. It says use numerical and graphical evidence to conjecture. What does conjecture mean? To calculate, figure out, or to guess. To make an educated guess is a conjecture. So to figure out whether the limit exists and what it appears to be if it does. So if the limit doesn't exist, then we don't have to do the other half of the question, right? Right. All right, so we've got this function, x squared minus 9 over x minus 3. I'd like for you to start by taking your calculator and putting this into your calculator. All right, so everybody have that inside of y equals? What I'd like for you to do is to go into the table just like we did last time. And you can clear out anything that's there by hitting delete on top of the x value. It'll delete out the values of x. All right, so last time we did something very similar to what we're about to do this time, but we didn't really talk about it in terms of limits. This right here says we want to take the limit as x approaches 3, right? Which means I need to take values that are close to 3 and getting closer. Right? That's what I did in my picture form, is that I took a value that sort of was close to where I wanted to be, and then I moved closer along the curve. So when we did this last time, under that premise, we did something like this. We started with something slightly bigger than 3, 3.1. And I said, okay, but I can get closer to that. Maybe I do 3.01. And if I get even closer with that same type of a value, I might try to do 3.001. Does that make sense? And then on the other side, see, these are values all slightly bigger than 3. I also need to do the limit from the other direction, which would mean numbers slightly smaller than 3. So something like 2.9, getting closer, 2.99, and getting closer yet, 2.999. You guys remember doing that one on the very first example last class period? Okay. So we're going to do that inside of our calculator now. So I'm going to do 2.9. Also, I'll do the 3 points first. 3.1, 3.01, 3.001. Is everybody's calculator cooperating with them okay to do this? Nobody's having any issues? Okay, good. And I have 2.9, 2.99, and 2.999. So inside of my table here now, I have 6.1, 6.01, and 6.001. And then over here on the other side I have 5.9, 5.99, and 5.999. What value am I getting close to? 6. This value comes close to 6, and this value comes close to 6. Both of them do. Not only that, but if you actually look at what we just did, this one is the limit of my function. I'll call my function f of x as x approaches 3 from the right, because these numbers are slightly bigger than 3, right? And this side was the limit as x approaches 3 from the left. And they both approach the same location, x equals, as x equals 3, gets close to 3, the y is getting close to 6. But here's what I want you to do in your calculator next. I want you to tell me what actually happens when you get to 6. So I want you to put 3 in your calculator, x equal to 3. And what does it says it doesn't exist. It actually says in your calculator what? Error. It says error in your calculator. Now look back at that function, and you tell me, why is it giving you an error? Because if I put a 3 in the function, I'll get a 0 in the denominator, right? And we can't divide by 0. Okay, you guys have had lots of math enough to tell you that that's not okay. Not going to divide by 0. All right, so this is interesting, right? So, I mean, the limit is 6, but the function doesn't get to 6. I mean, it doesn't even exist there. So what in the world is going on? I know some of you already know the punchline, so pause with me and give everybody else a chance to try and figure it out, okay? I want you to graph it next. So we haven't graphed together yet, so I want you to make sure your window looks like mine. I want you to do zoom, which is right in the middle along the top line. And we're going to pick zoom standard, which is number 6. That's our standard 6x6 window. What does that graph look like? Well, why in the world does it look like a line? Because that equation does not look like a line to me. What's really going on? All right, so somebody tell me, what is really going on? This location right here, what's happening when we get close to x equals 3? Do you remember from algebra? Yeah. There's a hole in the graph because of the denominator. Now in algebra, you found out in advance of drawing this thing on your calculator or whatever that there was a hole in the graph. Do you remember how you found that out? You found it out by taking this, and we're going to do this in section 1.3, by taking this function, this rational expression right here, and factoring the numerator. And if you factor that numerator, one of the factors matches the denominator, and what do you do with them? You cancel them out. And when you do that, you create a hole in the graph because you've eliminated a piece of the equation. So the graphical point of what's happening is that it still ends up looking like a line. And it looks like a line with a hole in it, but your calculator can't show that hole. And the reason it can't show that hole is because that hole represents a point, and points have no dimension. They have no width. They've no way to actually show that. I mean, it's not possible to show. And when we draw the graph, we do something like I just did here, where we put the little hole in there. We sort of give it dimension just for our sake, right? But we recognize it doesn't really have that dimension. So again, if I were moving from the left and from the right like I did on the previous screen, from the right-hand side, I would be doing this like I am with my red arrows. And from the left-hand side, I would be moving like I am with my green arrows. And I would be still approaching the same spot. I just wouldn't get there. Okay? So this is me and my husband both driving to Chili's in Shawnee, but somehow something along the way makes us stop in the parking lot and we never go in the restaurant. Or maybe we do and the wait so long we don't wait. Okay? We get there, almost. We still arrive, we're still at the same location, almost. Does that make sense? Because this is what it looks like from a numerical perspective and a graphical perspective combined. We're going to do another one. Now, what happened to this function? What changed? There's a plus in that numerator, and that plus is going to make a big difference in what happens. A big difference. All right, so let's put this equation in. In fact, if you hit y equals, all you got to do is change that sign right there to a plus. And if you didn't clear it out, you should be able to go into the table, and the table is already set up for you because you have those same y values already in that table, or that same x values already in that table. But the y values look a little different, don't they? All right, so let's see what we have. Same x values. We've got 3.1, 3.01, 3.001, 2.9, 2.99, and 2.999. And now my y values, they don't look quite the same. I have 186.1. I have 1806. I'm just going to write them down exactly like I see them right now. 18006. I recognize I could get more decimals out of there, but I'm seeing enough to know what's going to happen. And then I've got negative 174.1, negative 1794, and then negative 17994. And of course that 3 at the end on my screen here, right, is because we still recognize that we can't put the 0 in the denominator and get the 3 in there. Let's look at these on each side first. This is the limit from the right. What's happening? 186, 1806, 18,006. What's happening? It's getting larger, right? In fact, it looks like it's getting larger almost by a factor of 10 every time, doesn't it? That's actually what's happening. It's not just what it looks like. It really is. It's getting larger. So this one, and we'll talk about this more in a minute, this one looks like it's going to infinity. So for the moment, I'm going to write infinity here, although I know we haven't talked much about infinities. It's in the later lesson. But it looks like it's getting infinitely large, right? There's no specific number it's getting close to. What about the other one? This is the limit as x approaches 3 from the left. What does this one look like is happening? Yeah, they're getting infinitely large and negative, right? So this looks like it's approaching negative infinity. So what's the limit?
Doesn't exist.
There's not one. It just doesn't exist. This limit does. So this limit doesn't exist. Let's take a look at the graph. I want you to hit graph. You should still be in that negative 10 to 10 window. Your calculator does something weird. Looks like this. Now, you're only seeing part of the graph here, obviously, because you only see stuff happening on the left-hand side. The question may be what's happening on the right-hand side. So we would like to know what's happening out there further. So I'm going to just zoom out. So I'm going to hit zoom and select number 3 to zoom out and see if I can see what's happening as I zoom out. And then I actually can see the other half of the graph. This isn't a very good picture, but you saw it close enough in that hopefully you got the sense of what's happening. This piece is coming up and around and down. And this piece, if I move from the right in, is coming down and around and back up. So visually on my screen, again, not trying to be too specific, except to say that it looks something like this. Now, I know your calculator puts a straight line right in here. That straight line does not exist. Some of your calculators don't even have that. Some of the TI-84s probably don't. Does yours have it, Andy? No, yours does. Okay, but yours doesn't. And so there really shouldn't be a line there. And again, we're going to talk more about why later, but what's really happening there is what? Do you remember? What was that? There's an asymptote there. There's a vertical asymptote right in here. I'll do it on a green line of what's going on. And that's happening at 3, and we know that's because that 3 would make that denominator 0. So graphically, along this curve, if I was starting on the right-hand side, let me use a black dot since I drew a red curve, unfortunately. I shouldn't have done that. If I'm moving closer to an x value of 3, I'm actually, from the right, I'm actually going up this curve, right? I'm just going swooping straight up. And if I start on the left-hand side and I move towards x equal to 3, all of a sudden I'm going to be swooping downwards. And that's visually what's happening to justify the numerical values we were getting. Are we all good with that?
So on the first one, what would your answer be on the number 2?
Oh, I'm sorry, we didn't write it in there, did we? This one was 6.
Okay.
Yes, the limit was 6 on problem number 2. Because they both approached the same value. Again, you don't actually have to get there. That's one of the things that you don't have to do in order to have a limit.
It would be 6 and just like
The limit would be
your
6.
line.
Mm-hmm.
You have to explain what it is.
It depends on how the question's asked. If it asks you to justify it like this one does, you would write a couple of sentences that justify, kind of like what we've been talking through, why that picture matches that numerical description.
Okay.
Yeah. All right. This question's a little bit different. This question actually asks us to sketch a graph with given properties. These questions are fabulous. You know why they're fabulous? Because all you guys could have different answers and they could all be correct. Right? They make you think about the graph. So I want you to take just a minute and I want you to try and see if you can figure out what this is telling you to do. If you can't, it's okay. I'm going to show you an example of how it could look. But I want you to think through the information. They tell you f of 0 is 1. They tell you the limit from the left is 2 and the limit from the right is 3. So draw a picture in pencil, hopefully, in case you do make a mistake, of how that might look. Sorry. Okay, now there's one piece of your picture that will be the same for everybody. What piece is it? F of 0 is 2. What is that telling you to do?
Solid dot there.
Put a solid dot at the at what point? What is the xy coordinate? At the x coordinate 0, the y coordinate 2, right?
Is it 1?
Oh, sorry, 1. I'm reading it wrong. 1, yes. At the x coordinate 0, the y coordinate 1. So let me just put a little bit of a grid in here so that we're looking at the same spot. So this is actually telling me that this, I'll draw it in red, has a solid dot right here, right? That is the thing that has to match on everybody's picture. because that's what this is telling you to do. What happens on the other piece? So the other piece says that if I approach the x value of 0 from the left, I should be getting close to the value of 2. So not the red dot, right? Or the red dot. I'm not trying to get close to there. I'm trying to get close to the one black line that's above that, right? So there is going to be an open circle right here. And somehow I have to draw something that from the left-hand side gets close to this open dot. And that's where your picture can take its own nature of whatever you want to draw. You can draw any beautiful thing on the left-hand side of that you want. So if you want to draw a straight flat line, go for it. If you want to draw something curvy and fun, so we can do this, we can do this, we can do that. Whatever you want to draw, I'll stick with the last one I drew just because I drew it last. It can look like anything on the left-hand side. It just has to have that open circle at 2 that it's getting close to. All right, the other one says I'm supposed to be getting close to the y value of 3 from the right. So what am I going to do? Open dot at 3, you got it. And what am I going to do on the right-hand side of that?
Whatever you want.
Whatever you want. So there we go. Does that make sense? It's a little weird, right? And it's a little weird that we all get to draw our own picture. But there are features of that picture that are the same. There are pieces of that make it correct, and then we have flexibility beyond that. Any questions on that? I think there's one or two that you guys get to draw in this sort of a fashion too, where they give you some details and you have a little bit of flexibility and get to draw a picture. Right? Okay, that's the end